Hello and welcome to the Endurance Science Podcast. The aim of this podcast is to cut through the noise and misinformation that social media presents us and discuss what the science really says about endurance performance. I'm Matt Carpenter, a lecturer in sports science at the University of Northampton, just coming towards the end of my PhD, looking at endurance exercise performance, particularly exogenous ketones and their impact on exercise capacity alongside chronic ketogenic diets. And in today's episode, I want to go nice and deep into one of my favorite topics within sports science, and that is lactate. Lactate for many, many years and to this day is still mischaracterized as a villain within exercise physiology, when the truth is it is quite the opposite. And so that is the science I'm going to outline today. To set the scene, we really need to talk about how we talk about lactate and lactic acid in running and endurance communities. If you listen to the World Athletics Championships commentary coming up this summer or any major marathon, you will hear people talk about the burning sensation people feel, and they will talk about lactic acid as the villain. And often that's what people will associate with that burning sensation you get in your legs as you're getting towards the end of a 5K, end of a marathon, whatever it might be. Your legs are heavy, your breathing's running ragged, it's all over the place. And you're told by your coach, you're told by commentators on TV that it's the lactic acid building up in your muscles. But as I've said many a time to my students, and I love to talk about, it's not the lactic acid. And everything that I was taught about lactate as a GCSE and A-level student, and even through parts of my undergraduate, because it was 10 years ago now, is now considered outdated. In fact, lactate is not just a waste product of exercise. In fact, it's one of the most important fuels that our body has. Our body can use lactate for energy, and particularly the brain loves to use lactate. But it's more than just a fuel as well. It's a messenger that can tell our mitochondria to start producing more energy. And that's what some recent research has found. And so in this episode, I want to talk about the story of lactate from where it began as the villain of exercise physiology to where it is this present day, when it's more than just a fuel source, it's also a messenger within our body. This is the new science of lactate. So let's start with the story that I was taught as a student, particularly going through textbooks in A-levels and textbooks within exercise science that I was looking through as an undergraduate student. Now, the story we get, which is deeply embedded within endurance culture, goes something along the lines of this. When you exercise hard, your muscles start to run out of oxygen. They go anaerobic. And without oxygen, this anaerobic metabolism creates a byproduct. And that byproduct is lactic acid. The lactic acid accumulates in your muscles and causes a burning sensation that eventually forces you to stop exercising. When you rest up, your body can clear that lactic acid, you pay back the oxygen debt that you've created, and you can go again. And this traces back to a model that's over a century old that was created by A.V. Hill, who's very famous within the world of exercise physiology as one of the pioneers of exercise science, who ran some unbelievable studies, particularly for the time, on oxygen consumption during exercise. A.V. Hill studied runners and looked at their oxygen costs during exercise, and they proposed that the surplus was needed to clear the lactate that had built up anaerobically. And so lactate was the payment for borrowing energy without oxygen. It's your payment for anaerobic respiration. And it shaped how coaches design training programs and how people still discuss exercise physiology to this day. We've got terms like anaerobic thresholds, lactate thresholds, these being the intensity at which lactate starts to accumulate in the blood faster than it can be cleared, which to this day is a very useful metric to use, something that we test in our consultancy in the lab at the University of Northampton. But there is a problem with the oversimplification of the role of lactate. And I'll talk about this in future, the idea that whilst lactate thresholds are a really useful metric, it's not because lactate is bad itself. Just because lactate's high in the blood doesn't mean lactate itself is a villain. And this is really the issue, is that we saw lots of lactate in the blood, and we see lactate as therefore the baddie of exercise physiology. That's not quite the case. And a lot of this comes through the work of George Brooks. George Brooks is a professor at the University of California, Berkeley, and he has completely changed the way that scientists see lactate through his work over what must be 40, maybe even 50 years at this point. In 1985, George Brooks proposed the lactate shuttle hypothesis, at the time considered a radical out there idea. His argument back then, and that is now 40 years ago, argued that lactate isn't a dead-end waste product. It's a shuttle. It acts as a mobile energy currency that moves between cells, between tissues, and even between organs. And he proposed that lactate is producing fuels that other cells in the body, be it the heart, the brain, liver, the muscles, are all actively taking up and burning, using for energy. And so we can think about what that means. That means that during the long run, our muscle fibers are running primarily on glucose and creating lactate. But that lactate we're creating can then be recycled and used again for a fuel. Your heart can burn lactate, your brain can burn lactate. So lactate isn't accumulating because your body has failed or because it's a waste product that you need to get rid of. It's accumulating because it's being produced faster than it's being consumed, because we can consume lactate and use it for energy. And so George Brooks and his colleagues used isotope tracer technologies, very similar to what's being done now in the world of carbohydrate fueling research. And doing this, they demonstrated what was happening in real time during exercise. They labeled lactate with a carbon-13 isotopic tracer and looked at where that lactate went in the body. And they found that not only was the lactate that we create in the body being used during exercise, it's also being used and consumed as a fuel at rest. And since its inception in 1985, the lactate shuttle hypothesis has been advanced and advanced and advanced. George Brooks identified what he called cell-to-cell lactate shuttles, where lactate moved between producer cells and consumer cells via MCT transporters. These MCTs are proteins that sit in the cell membrane and transport lactate in and out of the cell itself. They also transport ketone bodies. And he also described an intracellular lactate shuttle, so a lactate shuttle going on within the cell itself, which suggests that lactate could be taken up directly by the mitochondria within the same cell it currently exists in and used for energy and oxidized there. And so for endurance athletes, many people listening to this podcast, the implications of this are substantial. And it may not change the way you train, but it will definitely change the way you think about training. Training at and around the lactate threshold isn't about learning to tolerate the poison that is lactate or lactic acid. It's about building your machinery to be able to utilize that lactate for energy, building the mitochondria, the MCTs, the enzymatic capacity to produce, shuttle, and consume lactate more efficiently. And there's some really interesting research from George Brooks's work that all endurance athletes should know about. And really, all endurance athletes or anyone interested in science should go and read some of George Brooks's work. And I'll link that in the description because there's some fantastic review papers that are not too dense, not too hard to read, but unbelievably interesting. And one example of their work is comparing trained and untrained participants exercising at the same power output. And what they found is that they produced lactate at more or less the same rate with some small variations. The difference was that trained athletes could use that lactate more efficiently. They cleared their lactate much more efficiently than untrained athletes. So their tissues were much better at picking up the lactate, taking it out of the blood, and using it as a fuel. But we can go beyond the idea that lactate is just a fuel source. There's emerging evidence that it's one of the body's preferred sources of fuel. And when it's present, the body preferentially uses it over other substrates. One example of this is a study published by Sheng Hui in 2017 in Nature. And they demonstrated that circulating lactate rather than glucose is the primary carbon source that's feeding your Krebs cycle. So when lactate is present, it acts as one of the primary sources of Krebs cycle entry. And the Krebs cycle is our key energy producing pathway for aerobic respiration, so respiring or exercising in oxidative conditions, which is what almost all endurance is predominantly focused around. So under normal resting conditions, lactate is contributing more carbon to our mitochondria than glucose does. This was true in the muscle, in the brain, and in the liver. And when we get to lactate concentrations of 1 to 2 millimolar, potentially what you might be doing during slow, fairly easy exercise, lactate is the second most abundant circulating carbon source after glucose. And that's because it's consistently being produced by glycolysis, which is our breakdown of glucose into pyruvate, which is how we use carbohydrate or glucose for energy. And so every molecule of glucose that goes through glycolysis is generating pyruvate, which can readily become lactate and then used for fuel itself. And because we're always breaking down glucose, we always have lactate available. And so if you're an endurance athlete out on a long run or a long ride, lactate is consistently transported around in your bloodstream, being produced by the working muscles and being consumed by major organs within the body. It's also being taken up by the liver and converted back into glucose via gluconeogenesis. People tend to associate gluconeogenesis, which is the creation of new glucose from a non-glucose source, with protein, because protein is broken down through gluconeogenesis into glucose. But it's not just protein that goes through that process. Lactate does as well. And that is through a process called the Cori cycle. Here, it's being used directly as an oxidative fuel. And our whole bodily system, and this whole system scales up as exercise intensity goes up. The harder you're working, the more lactate you're producing, therefore the more lactate you've got in circulation, and therefore the more your oxidative tissues rely on lactate itself. But this led to a question. And that question was, why does the body seem to prefer lactate in some conditions? For example, if glucose is available, why convert it into lactate, shuttle it around, and then oxidize it, use it for energy? Why not just send glucose directly into the mitochondria? And that is where some recent work looking at lactate as a mitochondrial messenger can partially explain this. And this paper was titled, "Lactate Activates the Mitochondrial Electron Transport Chain Independently of its Metabolism." Now, this is one of the most interesting papers I've read, honestly, ever. Because firstly, the methods were super interesting, and from their innovative methods, they were able to generate some really interesting conclusions. So let's talk about what they did and what they found. So what the researchers did was they used a form of lactate called D-lactate. It's the identical form of the natural L-lactate that we find in our body. L-lactate is a lactate you see in the body that our muscles and our organs can break down. D-lactate cannot be metabolized by humans. So they used D-lactate to see what happens when there's lactate circulating in the body that the body cannot use. And what they found was that lactate doesn't just serve as a fuel source. Lactate can actually turn on the electron transport chain, which is our ATP generating machine in aerobic metabolism, and make it run quicker, run faster. And it does this without even being metabolized. And they demonstrated this by showing that the D-lactate, which isn't metabolized, had this effect on our oxidative metabolism. And so the lactate doesn't even need to enter the Krebs cycle to impact our aerobic respiration. Its presence in the mitochondria is enough to rev up our oxidative machine during aerobic respiration. And what this means regarding lactate is that a molecule that the body couldn't metabolize or use as fuel was able to completely change the way that our aerobic system works. And how does this happen? The researchers showed that the lactate enters the mitochondrial matrix directly, independent of the mitochondrial pyruvate carrier. So it has its own way of getting in the cell. And once it's inside, it acted directly on the electron transport chain itself. And it seemed to be specifically targeting the electron transport chain. And the researchers also then showed that lactate's effect required oxygen. So it had to be under aerobic conditions. Under anaerobic or hypoxic. Under hypoxic conditions, lactate wasn't able to activate pyruvate dehydrogenase, or PDH. And beyond that, when they destroyed the integrity of the mitochondria, lactate's effect disappeared. What this tells us is that lactate isn't directly binding to pyruvate dehydrogenase and flipping a switch. It's activating the electron transport chain downstream to activate PDH, which is almost the reverse as we would expect. It increases the mitochondrial NAD plus to NAD ratio, and as a result, pulls more pyruvate into the Krebs cycle. And so what is the role of lactate here? What is the key takeaway? Well, lactate enters the mitochondria and stimulates the electron transport chain directly, possibly at complex 3. This itself increases ATP production. ATP is our body's energy currency, and so the more ATP, the more watts we can put out on the bike, the faster speed we can produce when we're running. This increased mitochondrial ATP then suppresses glycolysis itself, and the activated electron transport chain then, through the regeneration of NAD+, activates PDH, which pulls more pyruvate into the Krebs cycle. And since lactate is the main source of pyruvate in most cells, it effectively demonstrates that lactate stimulates its own oxidation. It's a feed-forward loop where lactate stimulates lactate. And so what does this mean for endurance athletes? People that want to get faster, get better on the bike, get better on their runs. Well, more than anything, it changes how we should see lactate itself and our lactate thresholds. The lactate threshold isn't just a point where lactate production exceeds clearance. It's our tipping point where your lactate signaling system has been overwhelmed. Below this threshold, our rising lactate levels are actually telling your mitochondria to work harder, pulling more pyruvate into oxidative or aerobic metabolism. This is suppressing glycolysis, which at this point is kind of wasteful. You're getting more ATP per glucose molecule. Your body is running efficiently, burning fuel and conserving glucose through the use of lactate. And above this threshold, when lactate is accumulating faster than the mitochondria can respond to the signal itself, you lose that efficiency. Glycolysis begins to run unchecked, and glucose is being consumed faster and faster and faster. As a result, we're generating less ATP per unit of fuel. And on top of that, it may partially explain why endurance training works in the way that it does. When you train in and around your thresholds, you're not just building more mitochondria, although you are building more mitochondria, which is through the process of mitochondrial biogenesis. You're also building a system that is responsive to lactate as a signal. More mitochondria means more electron transport chain complexes to receive the messages that lactate is sending it. On top of that, more MCT transporters means more efficient lactate delivery into the cell itself. And so the more you train, the more you're allowing your body to maintain that feed-forward loop where lactate stimulates lactate and helps you spare glucose. As a result, glycolysis is suppressed, fuel is conserved at higher and higher and higher intensities. And so this almost brings us to things like pacing strategies. During a marathon or a long ride, an Ironman, these kind of things, what you're really managing is your lactate. You go out too fast and you're flooding your system with lactate beyond what your mitochondria can process as a signal. You go too easy and you're not taking advantage of that lactate feed-forward mechanism. And so it gives you a kind of sweet spot, your sustainable race pace. This pace is the intensity at which your lactate production and mitochondrial response are at some kind of equilibrium. Each molecule of lactate produced is being sensed, the electron transport chain is being activated, pyruvate is being pulled into the Krebs cycle, and as a result, ATP is being produced oxidatively rather than through glycolysis. And finally, it means that those interval sessions you do might take a slightly different meaning. When you're doing your interval training, your lactate that accumulates during your hard efforts isn't just waste to be cleared out. It's helping prime your mitochondria for the next effort. Active recovery, things like an easy spin on the bike or slow jogging, will help keep your lactate circulating and available to signal the mitochondrial activation. So it's not just flushing out the lactic acid. In fact, the lactic acid itself never gets into the blood. And so to bring this together, for many, many decades now, George Brooks has fundamentally changed the way we see lactate. And that hasn't quite made its way into mainstream science discourse yet. Every time you hear a commentator mention lactic acid, it's a reminder that this science hasn't got out into the wider world very well as of present. But George Brooks has very successfully within the scientific community made the case that lactate, rather than being a waste product, is one of the most important metabolites in our body. It's a fuel, it's a precursor to gluconeogenesis, and as we now know, it's a signaling molecule that shuttles between cells, tissues, and organs. His lactate shuttle theory has fundamentally changed how we understand exercise and resting metabolism. And recent research has taken this even further, showing that lactate isn't just a fuel for our mitochondria to use as energy, it's also a messenger that is telling our mitochondria to turn on, activating our electron transport chain independently of its own metabolism, shifting energy production from glycolysis to oxidative phosphorylation, therefore conserving glucose and promoting the use of lactate-derived pyruvate as the preferred mitochondrial substance. And so, for an endurance athlete, the takeaway is simple. Lactate is your friend, not your enemy. Every interval session you do, every tempo you run, every time you push and feel the burn in your legs, you are accumulating some waste. You're not accumulating lactate waste. You're generating a metabolic signal that is creating more powerful, more efficient mitochondria that's ultimately going to improve your endurance performance. You're training your mitochondria to work on that feed-forward loop of lactate. And so the old story of lactate as a toxic waste is over. And the new story of lactate, not only as a mitochondrial fuel, but a master regulator of energy production, is just beginning. And hopefully we're going to hear a lot more about it in years to come. Thank you for listening to this episode. A little bit more sciencey than usual, but hopefully some interesting kind of science. You'll find in the show notes a bunch of what I consider really interesting and fairly easy to read papers when it comes to scientific research. If you've got any questions, then let me know. I hope you enjoyed this episode as much as I enjoyed preparing for it. See you next week.